Okay, hello everyone. My name is David Radice. I'm faculty at Penn State. I work on numerical relativity. Let me start by thanking the organizers for putting together such a nice workshop. I'm really excited to hear about the latest and greatest progress in the field. I was given the task of summarizing what has been done in theory and what are the next things that we should be doing. I think this is something that is very difficult to summarize in 30 minutes or 25 minutes. So I'm going to give you a somewhat subjective list of things that I think are important to do in the future, and a summary of some of the key results in the field, which is slightly biased towards the things that I've worked on in the past. So I'd like to start my presentation with this slide. I'm sure you have seen this image many, many times. Some of these figures were also in Alessandra's talk early this morning. This is, of course, the data we have for GW170817. I like to show it here, not because I want to go through all of these details and explain what they are, because I'm sure you already know this, but rather to remind you of the challenge that we face. We have a huge data set of data that needs to be explained. We are not anymore in the good old times where we could do theory in complete vacuum and speculate on everything. Now we have actual data to confront against. So on the one hand, our theory has to match the data. On the other hand, we are very ambitious. We want to answer complicated questions using this data. And to summarize, some of the key questions are, how did these binaries form? For example, what is the mechanism that form these binaries? More in general, what are their properties? What are their typical mass ratios, their typical mass ranges? How do neutron stars power gamma ray bursts? Are all short gamma ray bursts powered by neutron star mergers, or are there other sources? What are neutron stars made of? Are they made of just nucleons? Are there other more exotic phases of matter like hyperons, deconfined quarks, something else entirely? We don't know. And the last one is a bit more personal for me. This is not how I write it in my grant proposals, but basically we want to understand where gold and other rare elements came from. We think that neutron star mergers produce some of these elements. Do they produce all of it? And how do they produce it? Is most of the material coming from the accretion disk and was swirling around the black hole before being ejected into space by some MHD process? Or was this material ejected tidally prior to merger? The difference between these two ejection mechanisms is important because different mechanisms lead to different composition of the material, different paths for the arc process flow to proceed, different nuclear reactions are involved, and so on and so forth. So we want to answer all of these questions using the data, and the tool of choice for us is numerical relativity combined with, of course, analytic insight. This is what we know today about neutron star mergers. This is the same figure that Sebastiano has shown earlier. This is a summary of things we know about how neutron star mergers evolve. We know that neutron stars at LIGO Cs were in binary at some point. They inspiraled possibly for many millions of years due to the emission of gravitational waves. They came into the LIGO band. They evolved for another couple of minutes before merging. And then after merger is when things start to become very complicated. So during this presentation, I will mostly focus on the post-merger evolution, since the in-spiral has been covered very well by Sebastiano. And I will divide the post-merger evolution into short time after merger and long time after merger. I will define more clearly what I mean by short and long time. But for the moment, let me just say that something of the order of 10, 20 milliseconds after merger is what I call short, and long time will be something else entirely. Here at the bottom of this slide, I list the main physical mechanisms that are driving the evolution of the binary. At early times, gravitational waves are the dominant process, and together with that also nonlinear hydrodynamics. As we go forward in time, other effects become more important. Viscosity. When I say viscosity, most often we mean the effect viscosity due to MHD turbulence in the remnant, not the microphysical viscosity, although that may also be important. and neutrinos, the emission absorption of neutrinos coming from this hot remnant and into the accretion disk. So let me start with the first early post-merger evolution. This is the part of the post-merger evolution that we understand the best, because the evolution at these early stages is dominated by hydrodynamics that we think we can understand up to a certain point, and gravitational wave emission. So really what matters here is the bulk motion of the fluid, and this is something that we have a hope to resolve in our simulations. One of the first things we encounter when we study the early post-merger evolution is that there is immediately a bifurcation. So some binaries make a black hole immediately, basically without bounce. Other binaries instead form something that we call a massive neutron star, or a hypermassive neutron star, or a supramassive neutron star, depending on classification schemes. But they form a somewhat stable object that survives for a little bit of time before collapsing to black hole, or they may be stable forever. As Sebastian already mentioned, we now know that prompt black hole formation, at least for comparable mass ratio binaries, occurs when the total binary mass is larger than the maximum mass for a non-rotating neutron star, multiplied by some coefficient, this kappa, that in turn depends on properties of the neutron star equation of state, and most tightly correlates with the compactness of the maximum mass neutron star. For very different from one equal mass, so for very unequal mass systems, the dynamics is a bit different, and this is why I highlighted here the paper by Sebastiano in red, because this is where things really start to become a little bit different. Focusing on the electromagnetic counterpart, why do we care about prompt black hole formation? We care about it because we think that, at least for equal mass systems or comparable mass systems, prompt black hole formation implies no EM counterpart. So in other words, we have a hope that when we have sufficient number of observations and follow-up measurements of detections or non-detections of electromagnetic counterparts, we'll be able to pinpoint this threshold mass experimentally or observationally. And then since this threshold mass correlates with properties of the equation of state, we can invert this relation and then say something about the compactness of the maximum mass neutron star or the maximum mass directly. This is why it is interesting to look at prompt black hole formation. Why is it so that prompt black hole formation means an electromagnetic counterpart? This is illustrated in this figure I took from our recent paper. What is shown here is the mechanism for formation of the accretion disk and the ejection of material in the neutron star merger. If you focus for a moment on the lower part of the figure, here this is a case for an equal mass system. So what happens in these systems is that two neutron stars come together, a shockwave is formed when the remnant bounces back instead of collapsing the black hole. At this time, a lot of material is ejected. This is what we call the dynamical ejecta. And then as the system evolves, there is material that is squished out from the collisional interface between the two neutron stars that end up forming this accretion disk. So really what we call accretion disk in our simulation is probably better defined as an excretion disk, at least at early times, because this is material that is being pushed out of the remnant and has excess angular momentum and is heated up in the collision. If we have prompt black hole formation, then an horizon forms basically close to the time of the first image in the bottom panel, and the stars just fall into the common horizon. So there is no material left outside, all photons, neutrinos, everything is behind the horizon. So we don't expect any electromagnetic counterpart. On the contrary, if the mass ratio is large, we see that the secondary star is steadily disrupted prior to merger. So there is material that is ejected into space and forms, some of it is unbound, some of it falls back and forms an accretion disk, even if prompt black hole formation occurs. So these two types of events have very different consequences for electromagnetic counterparts. This is illustrated once again in this figure. This is a bit more quantitative. If you focus for a moment on the equal mass cases, these are the solid lines. What you see here is the evolution of the accretion disk mass as a function of time. You see that it follows almost a universal pattern. There is no material in the accretion disk prior to merger, obviously. And then as the stars merge, the mass in the accretion disk starts to grow. This is because material is being pushed out of the remnant. The growth terminates when there is black hole formation. You can see it for the SLY equation of state in blue, for less to 20 in red. At that time, part of the accretion disk is pressure supported, so this falls back into the black hole immediately, and some of the accretion disk remains behind. So what we see from here is that for comparable mass ratio binaries, the accretion disk mass correlates very strongly with the lifetime of the remnant. So in order to have large accretion disks, we need to have a long-lived remnant. If a black hole forms quickly after merger or promptly, then the accretion disk mass is very small or non-existent. And things are very different for prompt black hole formation. In this case, material starts to form a tidal tail even prior to merger, and the black hole forms from the accretion onto the primary star, which is already very massive, so it collapses to black hole, and then the disk just accretes with time. We think we understand these processes relatively well, and this is why we dare to fit the accretion disk masses with parameters of the binary. It turns out that at least for comparable mass ratio binaries, and here by comparable mass ratio, I mean up to mass ratio of about 1.2, this is where we pushed our simulations in these older works. We find that accretion disk mass correlates strongly with properties of the binary, and in particular, it correlates strongly with the tidal deformability of the binary. This is a parameter we have chosen for the reasons that Sebastiano mentioned before, but because this is the parameter that in the EOB and post-Newtonian theory describes matter effects of leading order in the inspirer, so we can hope that there is some kind of analytic continuation after merger, and this parameter remains important. And indeed, for comparable mass ratio binaries, we find that there is a strong correlation between accretion disk masses and tidal deformability on the one side. Electromagnetic observations provide a lower bound on the mass of the disk, or more in general on the mass of material that is left outside the remnant, simply because from observations one can sum up all of the energy released in the ejector, all of the radioactive contribution, then we know the rate at which material produce radioactivity, or to some approximation, of course. So from there, we can infer the total mass of material that is powering the kiloton of emission. And this turns into a lower bound on the accretion disk mass. So we have used this to start to propose a way to constrain the equation of state, combining electromagnetic gravitational wave observation. This is what we have done in this paper with Liang Dai. He is part of the IS group at the Institute of Advanced Study, which is a group that has developed their own independent tools to do gravitational wave data analysis. So as part of our collaboration, he has analyzed again the data for GW17017, just using standard gravitational wave data analysis. And here you see the posterior and the tidal deformability for this binary in blue. We reproduced the results from LIGO, but we have slightly different choices of priors and different choices in the analysis. So the results are not exactly the same, but very close. When we include the electromagnetic information in the likelihood, then we get a much stronger constraint on the tidal deformability. And in particular, we tend to rule out values that are smaller than about 300 at 90% confidence level, although there is a tail that goes down to 200. We can turn this into a constraint on the radius of the 1.4 solar mass neutron star using quasi-universal relations. And we find that our constraints would imply a neutron star radius of about 12 kilometers, give or take 1 kilometer. This is incidentally in very good agreement with what NICER has recently announced. So let me make a few comments here. First of all, here we have assumed that the mass ratio is not very large. If the mass ratio of this binary was very large, some of these conclusions will change, and Ken Takeuchi and collaborator have shown this very clearly. Where I think that what is most important is not really focusing on the constraint of the neutron star radius, because I think this is really a first step. We don't understand all the systematics yet, but rather to appreciate the potential of this method. Because as we do more simulations, we'll be able to, first of all, understand better how these masses change as a function of binary parameters, including not just the equation of state as we have done now, but also perhaps the mass ratio separately. So we have a pathway to constrain the equation of state, but also to constrain in principle the mass ratio of LIGO binaries by comparing EM observations and prediction from theory. And the other point I want to emphasize here is that the Bayesian framework allows us to include uncertainties. So we don't have to know everything about the parameter space of binary neutron stars to start constraining the physics. We can put our impose our changes in the priors that we use in gravitational wave data analysis, so we can change the likelihood only in the regions of parameter space that we think are well covered or well understood by numerical relativity simulations. But the main message here is we already are in a position where we can start doing multi-messenger astrophysics using numerical relativity. And the main reason for this is that in order to perform this analysis, we don't really need to know much about what happens long time after merger. We just conservatively assume that if you need, I don't know, 5% of a solar mass of material to explain the kilonova, you have to have at least 5% of solar mass of material outside of a black hole. So this is very conservative. We don't need to understand all the complicated physics that happens at longer time after merger. So here is where theory, I think, is currently successful, but still there is more work that needs to be done, especially exploring parameter space. Things become very different if we focus on the long-term evolution. And now I want to be a bit more quantitative about what I mean by long-term evolution. So I'm showing here for different binary neutron stars merger that we have simulated. On the y-axis, I'm plotting a typical time scale for gravitational wave emission. This is the angular momentum divided by the angular momentum loss rate as a function of the final angular momentum of the binary. Here, final is at the time when we stop the simulation, which is about 20 milliseconds past merger. What you can see here is that this time scale is at these times of the order of a second or more, and it's growing very rapidly. This time scale at the time of merger is a few milliseconds, and then as time evolves, this time scale becomes longer and longer and longer. And when we stop this simulation, the time scale is about a second. This is more or less the same time scale over which neutrino effects will play a role. This is also the same time scale over which viscous effects are expected to play a role. So when we consider evolution past this point, time scale for gravitational wave, time scale for viscosity, time scale for neutrinos are all comparable. We have in principle to include all of these effects in our simulations. We currently cannot really include all of them with the precision that we want. So the uncertainties from here on will become larger. This is another way to look at the same or a similar picture. What I'm showing here is not the angular momentum anymore on the y-axis, but the baryonic mass of the system. And these are the same angular momentum on the x-axis. These are the configurations at the end of our evolution. So when a gravitational wave emission time scale becomes very long. The gray area here, this is the all sets of possible equilibrium configurations. So what you can see from here is that even if we look at supramassive neutron stars, these are the ones that have total mass below the maximum mass for a rigidly rotating stars, these objects are all far away from equilibrium. So they will have to evolve in a non-trivial way to reach this gray area. And even objects that we traditionally call hypermassive because they have a mass above this maximum mass for a rotating star have a long way to go before they collapse, most of them. So it's very well possible that some of these hypermassive neutron stars may collapse. Others could instead get rid of sufficient amount of mass to reach this area of stability. And also in the opposite way, some supramassive neutron star may even collapse because of thermal effects. For example, we know that at finite temperature, the maximum mass for a rotating neutron star is larger than for a cold neutron star. So what I'm saying here is that we don't really know what is the long-term outcome of this evolution. We have to be very careful when we say example, GW19817 formed core rapidly, so it must have been a hypermass neutron star. I don't think that our knowledge of the post-merge evolution supports this conclusion at the moment. Probably its mass was closer to this threshold, but we don't really know. In the post-merge, there are many important nonlinear effects that start to become crucial. One is nonlinear hydrodynamics. There are non-axisymmetric instabilities in the remnant. One is the one-armed instability, the other one is a bar mode. And we have shown recently that these instabilities in the massive neutron star generate waves that propagate in the accretion disk. These waves are very effective in transporting angular momentum. And we find that the material ejected because of the injection of angular momentum in the disk by this mechanism has very interesting properties. This material is traveling quite rapidly and has an intermediate electron fraction. So we find that if the massive neutron star survives for time scale of the order of 100 milliseconds or so after merge, in principle, this spiral wave wind can imbibe sufficient material to explain things like the blue kilonova in GW17817 and the production of all R process elements, including light R process elements here with atomic mass number close to 100 and heavy R process elements. So this is a possible mechanism also for explaining R process elements. Another mechanism that becomes important, or another physical effect, is neutrino emission and reabsorption. Here I'm showing now classical paper by Sekiguchi and collaborators. They were the first to perform studies with neutrinos in full general relativity. I will not comment on the details here, but if you look at the scale for neutrino emission, luminosity is a few times 10 to the 53 ergs per second. This is a luminosity that is comparable, although not exactly the same as core collapse supernova. So we have quite large emission of energy in neutrinos. If we compute how much mass is in neutrinos after merger, this is about 0.1 solar masses. So if we look at the luminosity of 10 to the 53 ergs per second, this means that on a time scale of a second or so, all of the energy in neutrinos will be lost. So neutrinos could have an important impact both on the stability of the remnant, but also on the ejection of material and especially on the composition of material ejected after mergers. This is, for example, a simulation by Miller et al. This is the only simulation that really included everything for the post-merger. They didn't have dynamical space-time, but they considered a case around the Kerr black hole and fairly light disk, so they don't have to worry about space-time evolution. But in principle, the simulation included MHD and neutrino radiation transport with Monte Carlo methods. And what they find is that indeed these neutrinos emitted from the central part of the disk can be reabsorbed in the wind, can push the composition to higher YE, and in principle explain observations like the blue kilonova, but also explain the formation of light R process elements. There have been many other works in the literature on neutrinos, so I'm not going to be able to comment on all of them. But the general indication is that neutrinos are very important. They're crucial for nucleosynthesis, and they may even impact the stability of the remnant on time scales of the order of a second or so. The last effect that I want to consider for the post-merge is MHD effects and turbulence. This is something that will be, for many years, I think, very difficult for us to properly resolve and address. The issue here is that we know that there are instabilities that operate inside neutron star merger remnants that generate turbulence. And this turbulence operates on very small scales, especially inside the hypermass neutron star. We have a hope to resolve the MRI inside the accretion disk. For example, the simulations by Siegel and Metzger back in 2018 resolved the MRI in the accretion disk, and they show also this nice butterfly diagram where you see inversion, periodic inversion or quasi-periodic inversion of the poloidal field. Sorry, this is the toroidal field. That is an indication, this is a clear signature that there is a dynamo action driven by the MRI in the disk. It will be much more challenging to do something like this inside the hypermass neutron star. Nevertheless, we know that MHD effects are important, and they have at least two important consequences. One is they drive angular momentum transport in the disk. This is, if you want, a local effect that we can hope to fake or mimic with turbulence models. This is something I also tried to do in the past, and I'm also working on now. But MHD also has large-scale effects. For example, large-scale MHD stresses are known to generate winds and jets from these remnants. We know that if the central object is a black hole, the Blunt-Force-Nike mechanism is very efficient in launching jets. The simulation by Ruiz and collaborators showed that it is possible to launch jets in a jet in this configuration, so accretion disk formed in a binary merger and a black hole. We have also shown, oh, this is my timer for reminding me that I'm about to run out of time. We have also shown with Mosta and collaborators that it is possible to also launch a jet from a hypermassive neutron star, at least assuming that the magnetic field has some large-scale dipolar component that we, in this case, we introduced by hand. But the crucial thing here seems to be also to include neutrino transport in the disk, because we have done simulations that had no neutrino cooling, and in this case, the disk thermalizes, and there is a thermally driven wind that pollutes all the area at high latitude and basically prevents launching of a jet. So instead, with the inclusion of neutrino cooling, this area clears out, and we find the production of at least a relativistic outflow, so with Lorentz factor, terminal Lorentz factor of a few. This is not quite a GRB jet yet, but it's something promising. So in conclusion, I would say the two key messages that I want to leave are we have the early post-merger evolution more or less under control. This doesn't mean that we understand everything. There are many things we need to explore more in detail. For example, the impact of phase transitions, the impact of different mass ratio, spin, and so on and so forth. But in principle, the physics there is under control because the evolution is driven by gravitational wave emission. I didn't show the amplitude of the signal after merger, but the luminosity is in the 10 to 55 ergs per second. So there is no other mechanism that can really compete with that. So this is something we can address with simulations, and we can use already to do multi-messenger astrophysics. If we want to see something more about the long-term evolution of these objects, about how gamma ray bursts are launched, about the detailed composition of the outflows, then we really need to do better. We know that we need higher resolution simulations that include more physics, so both MHD and good neutrino transport, and we need to run for 10 times at least more than what we can do at the moment. So we have a big challenge that we need to address in the coming years. So the message here is that there is a lot of work to do. It's a good time to be entering this field. We'll have interesting results for the next few years. Thank you.
Thank you, wonderful. We have some time now for questions before we break out for lunch and then reconvene for the discussion session. So I see raised hand, Bruno and then Julian.
Hi, David. Thank you very much for the talk. A curiosity, in the case of the supramassive neutron star, do you think that doing an evolution, like a post-merger evolution in axis symmetry could help in understanding the evolution of those systems, or is 3D really necessary? I'm asking because in the past, several years ago, remember that Matthew Duetz did some simulations of what he called ultra-spinning neutron stars, which are essentially supramassive neutron star with a much larger spin than what you could have for a uniform rotation. So I was wondering if there is some trick we can use, like, for example, axis symmetric simulation, 2D simulation, in order to evolve those systems on a longer time scale, or not?
Well, I think there is a merit in axis symmetric simulations. There are non-axis symmetric effects that we find in our simulation. For example, this one-armed instability. They may change, for example, the rate at which material is ejected from the accretion disk. But if we are focused on the stability of the remnant, axis symmetry is probably already a very good first step. Because one of the things, for example, that I think we need to understand better is the role of realistic viscosity over long time scales on the stability of these objects. And this is something that we can in principle address with axisymmetric simulation. And the other is the effect of neutrino cooling on long time scales, because we don't really know what neutrino cooling will do. As I was mentioning, all of our intuition is based on comparing with isolated uniformly rotating zero temperature neutron stars, but neutron star merger remnants are not zero temperature. So we don't really have a good handle, I think, on what the fine temperature effects will do. I think it may be possible that the threshold for separating remnants that really survive for a very, very long time from those that collapse within a time scale of a second may be a little bit fuzzy and depend on microphysics.
Mm-hmm. There. So Julian, your question now.
Okay. It was an exceptionally clear, organized talk, but appreciated it. I'd like to go back to the slide where you showed the disk mass for a couple of examples of mass ratio and equation of state.
This one?
No, I think maybe the one before. Yes,
This.
that's the one. Right. And so my question is, you show quite a large contrast between two different equations of state. And the previous question and answer indicated that there could also be interesting finite temperature effects. So for equations of state that lie within the range consistent with the waveforms, how much play is there in the predicted disk mass for otherwise fixed properties?
So here, first, okay, this is not addressing your question directly, but I want to clarify maybe a point. Here, what we find is that actually, if you look at the behavior with these three different equations of state, the evolution of the disk mass with time is very weakly dependent on the equation of state. So where the equation of state enters is in setting the time for collapse of the central object.
What I was looking at here is both the contrast in disk mass at later times between the green and red curves, but also between the red and the blue.
Yeah, the blue curve here, what happens is at this point there is black hole formation occurs here, so we accrete big chunk of the disk at this point. And for the red curve, black hole formation occurs roughly at this point. And a big fraction of what we call accretion disk that we define as material with a density below 10 to the 13 grams per cubic centimeter, because this is where the isocontour of density changes from being roughly ellipsoidal to something that looks more like a disk. And this is also where the angular momentum, so the specific angular velocity peaks. But part of this material is really pressure supported, so this is why it accretes very quickly after merger. But apart from this point, to come more directly to your question, if we take the constraints that LIGO gives only, so the tidal deformability as inferred from GW 1708-17, and we look at the equations of state that we have, then the range in allowed disk masses is very large. It goes from 0 for GW 1708-17 all the way to 0.2, maybe 0.3 solar masses. If we include the disk mass as a part of the way in which we constrain the equation of state, then of course the range that we infer in possible disk masses decreases, but this is by construction.
Okay, thank you. All right, so I think there is another question, quick question in the chat. Tanasa, do you want to ask it? Sorry, Tanasa, do you want to ask your question?
Oh, yes. David, I'm a first year grad student at TTU, so I don't have much background on this, but I just wanted to know how sensitive the simulations that you were talking about are on the initial condition, because we don't know much about the initial condition when we are doing these MHD simulations. That's
That's
what
a
I
very good.
Sorry.
Yeah, this is a very good question. So our simulations are very sensitive to, or are sensitive to initial conditions such as the mass ratio of the binary and the spin of the binary. In principle, all of these results are also sensitive on our assumption of what is the eccentricity of the binary at the initial time of our simulations. In practice, I think there are very good reasons to think that for astrophysical systems, eccentricity will be very small. So we neglect this as a possible free parameter. So if we forget for a moment about MHD, I would say that we have a good understanding of what are the important parameters in the initial condition. And these are the equation of state and the binary masses and their spin. So it's the same as for binary black holes, but with the addition of the equation of state. For MHD, another issue is that we don't know the structure of the magnetic field inside neutron stars, and especially we have no idea about the magnetic field inside very old neutron stars that perform in binary and underwent all of the evolution over millions of years until they come into LIGO band. I think most of the MHD simulations used very simple idealized initial condition for the magnetic field, but we know that those initial conditions are not correct because typically most groups initialize just a poloidal field, which we know to be unstable. But there have been only little work on the sensitivity of the post-merger evolution to the structure of the magnetic field. I think maybe Bruno Giacomazzo or Riccardo Ciolfi, they have done some of this work. Maybe they can comment on this.
Okay. Okay, so given that I think we have a discussion session in the afternoon, we might want to leave some of these topics and open questions for later in the day. Indeed, I would like to ask everyone to think about before joining in today in the afternoon about anything you would like to hear discussed in the breakout sessions.